Bismillahirrahmanirrahim. Assalamu alaikum, dear students. In the third lecture of CASTEP series, in this lecture I will discuss further about CASTEP calculation setup. So in our previous lectures we discussed about setup, and here we will proceed our discussion to another type of CASTEP calculation, electronic. When we click on electronic, we get this type of interface in which we have different parameters: energy, cutoff, all of these cap points, pseudopotentials, relativistic treatment. I will discuss all of these parameters in detail. So we define cutoff energy as basically the minimum kinetic energy of a plane waves used to expand the electronic wave functions. Through this cutoff energy, we can control the accuracy of wave function expansions. We have different qualities in the options: coarse, medium, fine, ultrafine. It's depend on your calculations, what type of calculation you want to do. If you just want to check your file, you should apply coarse. Medium, increase your quality with the balance of your PC specifications. And fine, ultrafine used for supercomputers. So the another thing is SCF Tolerance. This is basically self-consistent field. Through these parameters, you can give a threshold for self-consistent field of the loop of iterations. This self-consistent field is basically ensure that the electronic density and total energy are stable before moving to the next step. It's all about one loop. The self-consistent field will give information about the electronic density and total energy of the system. As it's stable, it's okay for these iterations. After that, it will move to further. So in this option, we have also choices: coarse, medium, fine, ultrafines. And next thing is energy tolerance, in which we have atom and cell. This is basically the convergence requirement for total energy stability, either normalized per atom or the entire cell. So it's asking something about are you want to convert your energy, your stability about your atoms, you want to do this for entire cell. So through this you ensure atomization stop only when the energy is physically converted. So we have two options, atom and cell, and per atom means used when compare energies of differently sized system. When you have different size system, when you drop some element in your paper crystal, you should use this parameter for atom. If you want to calculate a single crystal, if you have a bulk lattice, so you should prefer to select on cell. Next we have cap points. This is basically the grade of sampling points in a bryozoum. Through this we can determine accuracy of integration or reciprocal space. If you give denser grade, your result will be more accurate, but it will take a lot of time. In this option we have also different options: fine, gamma, coarse, medium. Through this you can change your quality of calculations. The next thing we have pseudopotentials. The pseudopotential is basically elective potential replacing forced electrons, allowing only valence electron to be treated. Through this you can only treat the valence electron of the system. We have different options in pseudopotentials. So through this you can reduce computational cost without losing accuracy for valence interaction, in which we have different options: RTFG. RTFG means on the fly generated. Means flexibly you can automatically generate during running time, and like it's about ultrasoft or norm conserving. Or you just want to direct select ultrasoft or norm conserving. So you have different options in pseudopotentials. Ultrasoft is lower cutoff need fast, good for routine material simulation. If you want to more accuracy in your calculations, so the last one, the norm conservance, is more better, more accurate, but need high cutoff and will take a high time. That will need to have good specification of your computer. The last thing is relativistic treatment. Through this you can level of relativistic correction included in pseudopotentials. So we have different options in relativistic treatment: Schrödinger, Hamann, and 0. You select Schrödinger 1, so this is used for light elements like hydrogen, carbon, oxygen, etc. If you go to further want to calculate heavy elements, so you learn KHU will be in better form. And the last one, zero order regular approximations. This is advanced, including spin orbital coupling needed for heavy element. So in the last we have checkbox with use core holes, and through this you can create a vacancy in the core. If you want to simulate excited state in X-rays, absorption or core level spectroscopy, so this checkbox enable whenever you want to do spectroscopy studies. So it's no need to check out for geometry optimizations or ground. In summary, we can tell that cutoff energy is control numerical accuracy, CSF tolerance, control energy tolerance and convergence, pseudopotentials and relativistic treatment define physical model to study, and core holes. This checkbox is about used only for spectroscope, not for ground layer studies.